Okay, so we can start. We're happy to have Kurt Vinhage to tell us about partial hyperbolic actions of semi-simple groups.
Hey, well, thank you for the invitation to give a talk. Of course, please let me know if you need me to slow down and explain anything, but I anticipate that maybe you would want me to speed up based on the way that I prep my talk. So we'll see how things go. I'll give it as I prepared it, but we'll see how things go. Okay, so I want to start by describing some nice examples to motivate the theory and describe the types of behavior that we see from semi-simple group actions. So before we get into the rigidity parts of it, we should understand the examples that we actually see. So let me start with just one example. And I want to construct an action of SL3R on some higher dimensional homogeneous space of SLNR modulo a lattice gamma. So what happens here, I have this sitting inside of SLNR, and in this wee little 3x3 block, I want to put a copy of SL3R. And I want the action to be by left translations. So it turns out that whenever I have a left translation action on a homogeneous space, the dynamics of that action is always controlled by how the adjoint representation of the larger group sees the smaller group sitting inside it. So the dynamics of this action is controlled by big ad of SL capital NR, and then I want to restrict it to SL3R. So if 3 and n were both 2, this is the usual hyperbolic plane, geodesic flows, Horst-cycle flows, right? The Horst-cycle flows are unipotent, so the dynamics there is unipotent, and the adjoint representation really sees the quadratic separation in the orbit direction. The geodesic flow, the diagonal matrices, see the exponential expansion and contraction because this adjoint representation, which is the conjugation action, has two eigenvalues, the positive and negative. So what does this adjoint representation look like? Well, the adjoint representation acts on SLNR, the Lie algebra, which is just basically all matrices. The only condition I have is that the trace is not zero, and it breaks up in the way you might think it does. Here I see the adjoint representation of SL3R, and then I have a bunch of copies of the standard representation of SL3. And then here I have a bunch of copies of the dual of the standard representation. And then here I have several copies of the trivial representation. So if two elements of my homogeneous space differ along this direction, they see no separation, it's really isometric, there's no interesting dynamics happening that separates or spreads them. Here, things will exponentially separate according to, or drift apart according to the way that SL3R acts by the dual of the standard representation, and here by the standard representation. Any questions so far? So to understand the way that the dynamics of these semi-simple group actions, it makes sense to first understand these representations. And these representations are understood by looking at the diagonal subgroups. By restricting to Cartan subgroups. So these have maximal diagonalizable abelian subgroups. Because they're diagonalizable, representations of abelian groups that are diagonalizable actually turn out to be completely determined by their characters. So we classify representations based on the weights that appear. So the important data here are the weights. These are the weights of the rep. So in this case, the Cartan subgroup is the diagonal matrices, these are the T1. I guess I'm looking at SL3R, but you can imagine this to be some number less than big N. The weights of the adjoint representation, these are called the roots. So these are Ti minus Dj. So these are the roots. The weights of the standard are Ti. The weights of the dual of standard are minus Ti. And the weights of the trivial representation are 0. So these are the weights. And the main idea, right, if I call this A, is that if points differ in the corresponding weight space, corresponding eigenspace, the distance between AX and AY should grow like e to the I of A, or chi. R2 in this case, maybe diagonal to R is the weight. Right, so if I were to make this very simple and just look at the hyperbolic plane, right, then I have T1, T2. This is on the side. There are only 3 weights. There's the T1 minus T2, which is really 2T1. There's T2 minus T1, which is really minus 2 T1. And then there's the 0 weight, which is, there's 3 eigenspaces for this action. So these are sort of, depending on how your points differ, you see expansion and contraction based on the direction you're moving in your abelian group. So I want to come up with a dynamical way to characterize this. The things that I want to point out are the following. So key features. So if A is not in the kernel chi, then A expands or contracts every non-trivial weight space. And let me put here a union over all the exponents chi. Right, so I have a union of codimension 1 subspaces. So as long as I'm not hitting one of these walls, this A in the translation action is going to expand or contract the corresponding foliation. So if chi of A is positive, we see here that the distance gets expanded. And if chi of A is negative, then the distance gets contracted. So this is going to lead me to the definition of totally partial hyperbolic. That's the sort of key action, the key data that I want to extract from these actions. I want to somehow prove that these are the nicest ones. The definition. I want to start from the end and then get back to the beginning. So in the end, I want to give a definition for a G action being partially hyperbolic, but I want to start from the abelian subgroup inside it. So what?
Sorry, can you tell me what A is not in what? Sorry.
If A.
In their key features. Sorry. A is not in what? Sorry, I just couldn't.
Yeah. Sorry, it's. If A is not an element of the union over all weights of their kernels.
Oh, okay.
Right. So if it's not in any of these kernels, then every one of them, the only way that I don't see expansion or contraction is if this is 0, right? Because then the distance is really asymmetric. Mm-hmm. So let's say that I have a RK action on a manifold X, which is C infinity. That's the category I want to work in. I'm going to say that going to fix the distribution. Give our action a name, why not? Alpha. I have an RK action and I want to fix an invariant distribution for this action. I'm going to say that A in RK is partially hyperbolic, EC partially hyperbolic. If there exists a splitting of the manifold into a stable distribution, central distribution, which is fixed, and an unstable distribution. What do I want for the stable? I want that it's contracting, and I want that the inverse is contracting along the unstable. So I really want to see uniform expansion, and this A is also allowed, this lambda is also allowed to depend on A. So everything's allowed to depend on A, except for EC, which is why I put it here before as part of the name of the definition. So if you're familiar with the Nossoff dynamical systems, this is very similar to the definition of an Nossoff. I want one more thing. I want that the norm of dA restricted to EU is sort of in between these two. So it's the norm of dA restricted to, EC. These have A's. So the unstable is faster than the center, which is faster than the stable. So the center manifold has to sit in between the stable and unstable growth rates.
So what is the regularity of this manifold?
There is no requirement on the regularity of S and U. You can automatically prove that they're Holder with these assumptions. For C, I actually don't remember what we asked for, but I think you need to impose some regularity. I need to look it up.
So the other two are just continuous.
The other two are just continuous. In EC, I think I'm not assuming smoothness. I'm assuming probably Holder. Okay. So now I want to make use of this. I want to generalize this phenomenon that I have lots of them, right? This is saying that they're off a union of hyperplanes. And I don't want to quite make that assumption, although we'll be able to conclude it from this one. I want to say that alpha is totally partially hyperbolic with respect to EC, and I'm going to probably stop writing EC as I move throughout. If the set of A's such that A is EC partially hyperbolic is dense in RK. This is certainly true for these ones. This is an extremely strong assumption that we hope to be able to relax in the future, but right now I need it. That I really see this kind of behavior where lots and lots and lots of elements see expansion and contraction, and I'm never going to be able to get all of them, even all non-zero ones, because I always have in higher rank a kernel that separates, right? I have to transition from expanding to contracting at some point. And finally, I'm going to say a G action on X is certainly partially hyperbolic if its restriction to a Cartan subgroup, which is one of these diagonal subgroups. If you're thinking about SLN, you just think about the diagonal subgroup. Is totally partially hyperbolic. So this is a nice definition. It gives us a lot of structure, gives us existence of stable and unstable manifolds, lots of dynamical things come out of the assumption that we are totally partially hyperbolic. Here I get stable and unstable manifolds. I just need one more definition and I can finally state a theorem rather than just give examples. So last definition. So WS sub A of X is the integral manifold tangent to ESA, and the same for the unstable. Now, of course, distributions may fail to be integrable. I haven't assumed any regularity, but these dynamical properties automatically imply you get this integrability condition for the stable and unstable distributions. This follows from this stuff from the 60s or 70s. I think here's the cube that this partial hyperbolic dynamics has stable and unstable distributions which integrate. So alpha is called accessible if, so I'm not going to write any words, I'm just going to draw a picture. So X and Y are arbitrary points. So for every X and Y, I can find a chain of stable, unstable, stable, unstable. I can switch between.
So what is alpha? What kind of object is alpha?
Alpha is either a abelian group action or a semisimple group action. And I want to say there exists an A such that, right? So this is the stable distribution for A, the unstable distribution for A, right? And so on and so forth. And these should really be manifolds, not distributions, because they're actually living on the space. So I can sort of, turns out that once it's true for one partially hyperbolic element, it's true for all partially hyperbolic elements. Once I get accessibility for A, I get accessibility for every A. Happy to explain this afterwards, but I'm asking you to take my word for it for now. So now I can say the theorem, and then I'll give some context. The theorem. So this is Damjanovic, or Spatzier, myself, and Zhou. So I'm going to state the semi-simple version. So if I have volume preserving action on a smooth manifold, it's ergodic, totally partially hyperbolic, and accessible. Then up to finite cover. So I may need to pass to a finite cover of X. X is actually diffeomorphic to bihomogeneous space, like this. G embeds into H. And really, it embeds into the centralizer in H of the group K. Right, so it embeds inside of H in a way that commutes with K. And the action is given by left translation. In these coordinates after conjugating by this diffeomorphism. So these are the only things you need to conclude that your action is actually algebraic. Some of these may be able to be relaxed, but this is the state of the art for the uniformly hyperbolic case. So let me give a few comments on how this fits into some other theorems in a similar direction, and then I'll try to talk a little bit about the proof. Any questions before I move on? Yeah.
You're assuming C infinity?
Yeah. Yes. C infinity action. I think we can go down to C2, but for safety, let me assume C infinity. One of the remarkable things about our technique compared to the KAM techniques is that we can work in very low regularity. So in the sort of precursor to this result, we could get all the way down to C2. I think we have the same thing here. Any other questions?
There you really need that the point where is the derivative in there's a bound on the derivative. This bound, do you need it on A, or can you replace A by a multiple?
Yeah, so I can do this.
Okay, that's enough. Okay.
This is enough. me. Yeah, I just wanted to state it simply. So, but yes, this is enough to get what we need. Any other questions? Okay. So this fits into a collection of results called the Zimmer program. And the Zimmer program has a much more ambitious goal than what we did, which is to classify all G actions or gamma actions, where gamma is a lattice in G, with G high rank. And I forgot to put that here. I need the real rank of every simple factor of G. So let's, for simplicity, let's assume that G is simple and that the real rank of G is at least 2. So the main idea that stemmed from is Zimmer's cocycle superrigidity. Which has this main idea of saying that, right, remember I said that the dynamics is controlled by the adjoint representation, and the adjoint representation is controlled by weights. So Zimmer cocycle superrigidity gives us access to the tools of representation theory. It says that there's a measurable framing for which the dynamics is really described by representation. Right, so this says that if G preserves a volume, or a measure, there exists a measurable framing such that the tangent bundle to X the action on the derivative action is given by a representation. Up to compact noise. Now, the key things that we're going to be using in our approach to proving the theorem is sort of the exponential, right? We're in the hyperbolic world. We're really going to use expansion and contraction. Compact groups can't really do that. So the compact noise doesn't bother us in our tools for later. So I can sort of understand the expansion and contraction directions purely by looking at the representations of G. So it's a very powerful theorem, but this is evidence that G actions are extremely limited. Right. Finite dimensional representations are really nicely classifiable by their weights. It's going to be very difficult to construct an action that has this property. Now, as a tool, it is an extremely nice tool, and it has been used by several people to prove rigidity results. But the thing you all have to overcome is this ugly word, measurable. The fact that your framing is only measurable means that if you want to use this framing to, say, induce a Riemannian metric or something like this, then Riemannian metric is only going to be measurable. So in this direction, there are several results. There are Brown, Fisher, and Hurtado, who's solved Zimmer's conjecture in 3 papers. Zimmer's conjecture is basically looking at this when you have the most trivial case possible, that there's no representations that actually appear. Because this is all given by a representation, if the dimension of your manifold is smaller than any non-trivial representation, you know that you have to have only copies of the trivial representation that appear, and your action is by measurable isometries. So they show that if the dimension of M is less than the minimal dimension of a representation of G, every gamma action on M is factors through a finite group. So this is sort of the other extreme. So they, rather than assuming some sort of additional structure on their dynamics, like some uniform hyperbolicity, as we're assuming in this theorem, they assume that there is no uniform hyperbolicity, that somehow your dynamics is so small, your manifold is so small that it's going to be impossible to see any expansion or contraction. And they work hard to use the group theoretic properties of the lattice gamma and G to prove that this measurable metric is actually has high regularity. There are several other authors and things that I could describe here, but I'd like to move on to discussing elements of the proof and how we leverage all of these properties. So what are our methods? So step 1 is to, well, we do exactly what they do. We need to assume volume. One of the reasons we need to assume volume is to be able to apply this. If G doesn't preserve a measure, there's nothing to say here. So we leverage Zimmer to get measurable metrics. On sort of measurable eigenspaces E chi, such that if I push a vector forward from one of these spaces, it expands exactly according to the dynamics or the weight chi. So chi is a weight of a representation that appears in the Zimmer cocycle superrigidity representation. So this is for all A and A. This is the Cartan subgroup, the diagonal side. Now again, I have this annoying word measurable. And in some contexts, measurable things are nice and pretty, but in this context, it's not good enough. So step 2 is to upgrade this. Right. Oh yeah. Step 2. So upgrade the metric and the regularity of of E chi using the so-called invariance principle. Version of the invariance principle we use is by Avila, Santa Maria, and Viana. But this was could be originally attributed to Le Drapier. And this is where we need this assumption. And this is really the only we'll use it one more time, but in step 2, this is sort of the key place that we use the accessibility assumption.
What does the invariance principle mean?
So the invariance principle says the following. So it says that if so there's a variety of versions. So let me state the moral. The moral of the invariant principle is that if a structure has a measurable solution over a partially hyperbolic accessible dynamical system, then it has a continuous solution. So we use this in a few ways. We first apply the invariance principle to conformal structures.
Also, that the structure has never as a solution.
I mean, so if there's an invariant measurable object associated to a system, then that regularity can be improved to Holder or continuous. So they show that it's a very general phenomenon that if I have a section of a bundle and I can prove that the solution is continuous along stable and unstables, and sort of I can get anywhere with stables and unstables, then that actually extends to a continuous solution everywhere. Now you need assumptions to do this, and we have to carefully check these assumptions. We can't apply it without checking them, but this is the main idea. Yeah.
So you don't just do this on a large measure set. Somehow accessibility actually gives you everywhere.
Exactly. I need volume preserving here. Thanks. So volume preserving is going to allow me to disintegrate volume and know that I have a solution at almost every point of the unstable leaf, right? And then through stable holonomies, basically, as long as I can produce a solution or show that the structure or section is invariant under stable holonomy, I can prove that it coincides with a continuous thing along the stable and unstable distributions. And sort of, I can continue extending it this way, and I just need to check that if I have a measurable solution, then this is actually consistent. This is a really difficult thing to do. The gap between this paper and this paper is at least 30 years. So there are lots of ideas that go into this. I don't mean to say that this part is trivial. There are lots of conditions to check, but this is the main idea. We have these nice measurable structures. The benefit of accessibility is allowing us to upgrade those measurable structures to Holder ones. Note that I'm not assuming any smoothness. This is really just measurable or continuous. So, and this is sort of as I mentioned before, the strength of the method is that it allows us to work in this extreme low regularity. We never really get past continuous at several points of the arguments. All right, so we can do this for conformal structures. We can do this for invariant subbundles. So if I have a measurable invariant subbundle, like E chi, I can upgrade it to now a continuous invariant subbundle. And I can even do this for the associated metric along that invariant subbundle. Right, so this measurable data can all be upgraded to continuous data using the invariance principle. One of the key things we have to do is from the accessibility of the G action, actually get accessibility of the so-called kernel action. So you have the E chi, you freeze the kernel, so you freeze it, and that's going to basically give you the center bunching that you need. One of the key things you need to apply the invariance principle is bunching of your data. So you need not only accessibility of A, but accessibility of elements of the wall here too. This is something you can arrange. Unfortunately, I have to give only brief sketches, but this is sort of one of the key ideas. Okay, great. So now I have continuous metrics that expand on the nose according to some weights of a representation. Step 3, I think, is the most innovative step compared to what Ralph and I did in a simpler context, which I like to call unwinding. So let me draw a few pictures to indicate what I mean by this. So let's suppose I have point X, and one of these I integrate E chi. So right, I have this foliation that's tangent to the Lyapunov distribution. And technically I should say coarse Lyapunov distribution, but for simplicity, I'm going to overlook this distinction. Now, what do I want to do? I want to, rather than trying to produce a homogeneous structure on G all at once, I want to do it bit by bit. So I want to sort of prove that this W chi has some homogeneity properties to it. In particular, I want to prove that with respect to this continuous metric, it's actually a nice system. So what do? I start moving by the action. But I don't want to move by an arbitrary element of the action, because that's going to do some bad things for me. I want to move by A and the kernel of this functional, this weight chi that appeared as part of the Zimmer representation. So what happens if I do this? Well, if chi is 0, then this is 1, and I really am just preserving the metric. And I can sort of, using ergodicity, come back to an arbitrary point. For a generic X, I can come back to an arbitrary point Y in the same leaf. And using the theory of non-stationary normal forms, I can conclude that if AKX converges to Y, then F, which is just defined to be the limit as K goes to infinity of AK, this is going to be a function from the coarse Lyapunov leaf of X back to itself is going to be an isometry such that f of X equals Y. This is what Ralph calls the high rank trick. It's used constantly in settings like this, right? I have some leaf that if I didn't choose the kernel, things would shoot away and this transformation would blow up. So the ability to sort of control the dynamics using non-stationary normal forms to get convergence, as well as maintain that the derivative doesn't blow up. These two things together give me convergence of this return as an isometry. And in particular, the isometry group of W chi of X is going to end up being transitive, act transitively. And not topologically transitively, like dynamicists like to talk about. I mean, in transitive in the group theoretic sense, any 2 points are linked by an isometry. Now, if you were like we were when we first started working on this, you'd say, aha, I found a nice parameterization of my Korsakoff affiliation in the homogeneous picture, in the bihomogeneous picture. This is exactly given by the parameterization according to a unipotent orbit. I've produced a way to describe a group action parameterizing these foliations. But I want to convince you that we're not quite done. This is not the action that we were looking for. And I want to draw the same picture that I did over there, but in the homogeneous setting. So let's start from a point P gamma. Now I want to translate by A. And I want to come very close here. And let's say that it comes back to, right, this is parameterized by some unipotent group orbit, G gamma. So let's say that this is U G gamma. So what happens if I do this? I get AK G gamma converges to UG gamma. So let's see what happens if I drag a point along with it, right? I'm saying that this is an isometry. Let's take a different point, VG gamma. This is connected by V, and let's just drag it along, right? This is an isometry. The dynamics is actually going to commute with this as I go, right? So pull this along. Hopefully this is still VG gamma. Let's check and see what happens when I do this. Well, I want to take the limit of this sequence of transformations. So I take AK VG gamma and I see where it goes. But the fact that it's in the kernel means that it actually commutes. Right? At the group level, AK and V commute if it is in the corresponding kernel of the weight. Or if AK is in the kernel of the weight associated to V. So this is AK V AKG gamma. And I've already chosen AKG gamma to converge to UG gamma. So what's the issue here? I have now a function f of VG gamma. This is VUG gamma. It's inserting the U between V and G. This is really bad, right? This is actually not going to define a global action in my manifold. I can locally define it, not even locally, I can globally define it on a single leaf. But right translation isn't well defined on the homogeneous space. It's only because the leaf is simply connected that I can actually do this. So what do I have to do? I have to turn this left translation or right translation into left translation. And how do you turn right translation into left translation? You look at invariant vector fields. Right, so what's the trick to produce the parameterized group actions? The trick is to consider vector fields invariants under the isometry group of this W chi of X. And then you take the flows generated by those things. This is a Lie algebra, isomorphic to sort of the dual of this guy, right? Left invariant and right invariant vector fields have the same Lie algebra. It's It's the standard Lie algebra effect. And this turns what ends up being my right translation in the homogeneous case into a left translation, and that's exactly the action that I wanted to build. Now, what's the main problem? The main problem is that, okay, at every point, I can now associate uniquely a vector field. If you give me a vector at this point, I can sort of move it around by the isometry group, build a vector field, and then start pushing it. But I need a way to frame the vectors at the point. And this is exactly why I see this K appearing. If I didn't need to do this, then this K would just be trivial. But the K, this is why I call this unwinding. I need to build a principal bundle over the action. So of framings of each chi. To define actions parameterizing WK. So I build an orthonormal frame bundle, which is a compact group extension of my space X. And once I know the framing and I know how to turn a frame into a collection of invariant vector fields, now I have a way to move along those vector fields and really produce group actions on every coarsely up and off leaf. It's a technical procedure, but this is sort of the main idea. The cartoon you should have in your mind is that of geodesic flow on hyperbolic tree space. So of course, if you give me a single vector in the unit tangent bundle to hyperbolic tree space, I know how to build the geodesic through it. And I know that if I look at the Hor sphere through this point, that Hor sphere is going to get contracted as I move to the future. But I don't know how to parameterize it until you give me a framing of this space. So in fact, it's going to be impossible. There is no single action parameterizing the coarsely up and off leaf without doing this unwinding of the frame bundles. You need to pass from the tangent bundle to the frame bundle, and that's what we do in this step. Now note everything here is still continuous, but I can still define group actions. And that's kind of a remarkable trick. I have till, am I done or do I have till 5:30?
5:30.
Okay, great. I just want to say one word about the final step. Oh. Step 4. I'm on 4, right? Yes. I'm going to assume that I'm correct. That's what I have in my notes. Factors. So now because I have this nice conformal structure on each of these things, the RK dynamics also lifts to this principal bundle. So I have lots of group actions on this principal bundle now. I have RK acting on the principal bundle. I have UChi acting on the principal bundle for every root chi. or for every weight. I call it a weight guy. And sort of the fact is that accessibility is going to imply that we can get anywhere following the UCI light. So in the picture of accessibility over here, I use stable and unstable manifolds, but the stable and unstables are sort of subfoliated by the weight spaces, right? A weight will be stable if it's negative and unstable if it's positive. So if I can get anywhere with stables and unstables, I can certainly do it with these new group actions that I've built. So what's the idea? The idea is that if this is really going to factor through a group action, I just need to sort of include all of these. There's one other group that I need to include, and that's K. This is the structure group of the principal bundle. Right, I had to do this unwinding procedure. There are examples in which, even if your dynamics is accessible, after you do the unwinding, you lose this accessibility property. So for some actions, the one that I gave at the very start of the talk, this isn't true, right? It still persists after I unwind, but there are actions in which, so I have to include K. So what's the main idea behind these path groups? I want to let P be the group freely generated by RK, capital K, and UK. And here pi ranges over all of the possible weights. And P, because this is sort of free, there's no relations among these. Whenever I have a group action of these guys, right, just like the universal property of free groups, the same thing is true for free products. So P is going to act on Roman P. And it's going to act transitively by this fact. So the main difficulty that we have to overcome here is that we show that there exists S such that P mod S is Lie. And S acts on X truth, it fixes every point. So we find this co-Lie subgroup inside. These are all Lie groups, right? So it's a difficult thing to wrap your head around, but this three products of Lie groups is a topological group. It's a factor-connected topological group. It's a CW complex, but it's infinite dimensional. So in order to get a nice homogeneous space like this, I just need to turn these actions and factor through a Lie group. So we identify this big subgroup S inside. I don't have time to go into the details, but I'm happy to discuss tonight or tomorrow. And of course, the last thing we need to do to get back down to X is factor by K, right? P is an extension of X by K. So if I factor by K here, I really get that X itself was a quotient of a homogeneous space by K. And the dynamics, because it's by virtue of the facts that I've included RK in this list, the dynamics is included. There are some remaining steps in terms of upgrading the regularity of this Lie group action, P mod S. This is sort of standard. It's not new to us. And proving that just because we've intertwined the RK action, that secretly some of these UChi's were the root subgroups as well. That's not obvious from us, but we sort of reconstruct the rest of the G action as part of the action on X. Okay, I'll stop here. Thanks.
Sorry. Is it simple to see that if you have there exists A, you can get for all A or almost every A or something like this?
Yeah, so you get it for all of the partially hyperbolic A's,
Okay.
and that's because you can prove that WS A of X has this product structure. So it's homeomorphic to the product of what are called, of course, the Lyapunov affiliations. Chi1 cross W chi2 cross W chi n, where the chi-i's are such that this is negative if I'm doing the staple. So I move along chi1 and then chi2 and then chi3, right? So these are all transverse, so they sort of build an open set. And sort of, once I get this, it's equivalent to accessibility of the Lyapunov affiliations.
Yeah.
And then, so I can jump back and forth between N and A. It's just cleaner to state this way if I fix it.
Can you say something on the technicalities in the advanced physical?
Yeah, so what are the technicalities in the invariance principle? So the first thing is the conformal structure. I did a slight lie here in that I sort of conflated the Lyapunov affiliations and the Lyapunov affiliations. I really need to consider all the things that are positively proportional. And if I were to try to do it for an arbitrary partially hyperbolic element, I would be in trouble. So this is why I need accessibility of the kernels, which means that these are all zero. And I have now a conformal structure that's on each Lyapunov distribution, right? If this one is expanding by rate of 1 and this one is expanding by rate of 2, it's not going to work. So the key thing that you need is that the dynamics along the fiber have one exponent. This is the assumption that appears in Avila Santa Maria Brianna. So I don't see something that expands at rate e to the t and something that expands at rate e to the 2t. Everything sort of has the same expansion rate asymptotically. And this is the assumption of ASV. So the main idea is that if I choose A in the kernel of chi, and D is data associated along W chi, right? Then this implies that I, in fact, have better than one exponent. I really have zero exponents. And this is sort of the key thing that makes this argument tick. Without this, we wouldn't be able to cite their tools.
Is there any hope that you can treat lattices in Lie groups, or do you need the kernels too much?
That's a great question. We hope to be able to get there eventually. If you replace this partially hyperbolic by an Alsoph, then you don't need accessibility. And if we instead say there exists one Anosov element, this is work in progress. Now, this may seem like not related to your question, but I want to convince you that it is, because if I have a lattice action, I can still apply Zimmer. I can get the measurable things. But even if I have many, even every element of my lattice is an Anosov, I don't know how to show that I have Anosov directions in G. So even just getting one Anosov, going down the one Anosov direction in G is one step closer to being able to do it for lattices. But this is the difficulty, is being able to translate, at least with the approach that we have been trying, which is to go to the suspension. Suspension gives you access to kernels, right? So you just need to translate the Anosov or uniform hyperbolicity properties of gamma into G, and this is kind of a mess. It's very difficult.
Okay, if there are no more questions, let's thank Vlad again.